In a shocking astronomical discovery, the James Webb Telescope has unearthed 6 fully formed galaxies in an earlier time frame of the universe.
That we didn't know before, and of course the big answers are the first galaxies grew differently than we expected, and we don't know why they're.
The James Webb Space Telescope, with its towering gold-plated mirrors and deep space vision, has once again stunned the scientific world. Recently, it peered into a seemingly ordinary patch of sky and found something that has ignited a frenzy among physicists, cosmologists, and astronomers alike. The discovery? Galaxies. Massive, mature, fully formed galaxies that appear to exist far earlier in the universe's history than current models of physics can explain. These galaxies are not supposed to be there. Not at this time, not in that form, and certainly not in those numbers. Their presence is nothing short of terrifying because it shatters the very frameworks that scientists have been building for nearly a century. Before we start, smash the like and subscribe buttons for more updates. What Webb saw was more than just a blur of ancient light. It was a window into a time barely 300 million years after the Big Bang, a time when the universe should still be dark, chaotic, and just beginning to take its first structured breaths. Yet staring back from the depths of the early cosmos were galaxies brimming with complexity, spiral arms, heavy elements, signs of mature star populations, and in some cases, supermassive black holes already formed at their centers. These were not fledgling clusters of gas and dust. They were structured, organized systems, fully functioning galactic entities that had no business existing in an era when the universe was still, according to current theory, in its cosmic infancy. The implications of this are staggering. According to the standard model of cosmology, which is grounded in Einstein's general relativity and the lambda CDM model, structure formation in the universe follows a very predictable sequence. First, the universe cools from the initial burst of the Big Bang. Then, after a few 100 million years, matter begins to coalesce under gravity into the first stars and proto-galaxies. Over billions of years, these proto-galaxies merge and evolve into the majestic spiral and elliptical galaxies we see today. Webb's images, however, suggest that this process may have occurred exponentially faster, or in some way entirely different than previously believed. The sheer mass of some of these early galaxies is enough to raise eyebrows. One in particular appears to be as massive as the Milky Way, but formed just 350 million years post-Big Bang. To build up that much stellar mass so quickly defies the limits imposed by known astrophysical processes. Star formation has a bottleneck. Gravity must pull gas together to create stars, but feedback mechanisms from early stars, such as radiation pressure and supernova explosions, typically slow this process down. Yet here are galaxies that seem to have sidestepped or perhaps ignored these natural breaks entirely. To make matters more complicated, several of these early galaxies show evidence of metal enrichment, meaning their stars had already gone through life cycles and produced heavier elements like carbon, oxygen, and iron. That means not only did the first generation of stars form rapidly, but they also lived, died, and seeded subsequent generations within a time frame that stretches the limits of what's considered cosmologically possible. This points to an accelerated timeline for cosmic evolution, one that existing models cannot reconcile without invoking radical new physics. But the real shock comes from the presence of massive black holes at the cores of these primordial galaxies. Conventional wisdom holds that black holes grow from the remnants of massive stars, slowly accumulating mass over time through accretion and mergers. Yet some of the black holes detected in these early galaxies are already supermassive, millions, even billions of times the mass of the Sun. There simply isn't enough time in the early universe for such growth to occur through known mechanisms. This has led some theorists to suggest the existence of direct collapse black holes, hypothetical entities that form instantly from the collapse of massive gas clouds without the intermediate stellar phase. But even those models are strained by the scale and timing of what Webb has revealed. This discovery has effectively tossed a wrench into the machinery of modern cosmology. The cosmic timeline must now be re-evaluated. Were galaxies forming much earlier than we thought? Is there some missing piece of the puzzle? An unknown force or particle that accelerates the formation of large-scale structure? Could dark matter or dark energy behave in ways we have yet to imagine? Or are we looking at something even more profound, a fundamental flaw in our understanding of physics itself? Some researchers are daring to propose that the solution may lie in modifying general relativity or introducing entirely new cosmological models. Others believe that this might be evidence of physics operating differently under extreme early universe conditions, perhaps governed by quantum gravity or other exotic phenomena we haven't yet observed directly. Whatever the case, the shockwaves from this finding are being felt far beyond astronomy. Theoretical physicists are being forced to go back to the blackboards. Models that have been taught and refined for decades are now under review, their assumptions scrutinized, their equations tested against this new and unsettling data. The enormity of Webb's discovery also ripples into the philosophical realm. If our understanding of the universe's birth and growth is incomplete or incorrect, what else might we have misunderstood? Are there epochs of cosmic history that are fundamentally unknowable through our current scientific lens? Could there be layers of reality that we've never even thought to look for, simply because we assumed they didn't exist? Adding another layer to the mystery is the quantity of these galaxies. Webb didn't just find one or two anomalies, it found dozens in just a small portion of sky. If these early mature galaxies are this common, it suggests that the universe was far more efficient at creating complex structures than we ever imagined. The cosmos may have emerged from its primordial fog, not as a slowly organizing soup of matter, but as a place where stars and galaxies erupted into being with ferocious speed and order. This suggests a cosmic blueprint that differs dramatically from the one drawn by current theory. Instruments before Webb, such as the Hubble Space Telescope, were limited in their infrared capabilities. They couldn't see as deeply or as clearly into the early universe. Webb, with its massive 6.5-meter mirror and sensitive infrared instruments, was designed to pierce through the cosmic veil and illuminate the universe's first billion years. Yet even the scientists who built Webb did not anticipate this. Its precision has delivered not just better data, but data that calls into question the foundational principles used to interpret it. The broader ramifications touch every corner of astrophysics. Stellar evolution, black hole formation, dark matter interactions, the nature of time and space. Nothing is immune from reevaluation. Already, research teams are scrambling to replicate and verify the findings. If these galaxies hold up under further scrutiny, it may initiate a paradigm shift not seen since the discovery that the universe is expanding. That realization, which gave rise to the Big Bang model, changed everything. Webb's revelation could be the next such turning point, forcing us to revise or even replace the cosmic story we thought we understood. This is not merely about explaining away a few oddball galaxies. This is about the scaffolding of the universe itself, how it forms, evolves, and exists. It raises the haunting possibility that we've been peering at the cosmos through a fogged lens, constructing our theories from partial truths and incomplete evidence. If galaxies were able to form in such numbers and maturity at such an early stage, perhaps we've underestimated the forces at play or overlooked critical variables that shaped cosmic history in ways we never imagined. There's also the curious question of what this means for the concept of cosmic inflation, the brief period of exponential expansion believed to have occurred moments after the Big Bang. Inflation was proposed to explain the uniformity of the cosmic microwave background and the distribution of matter in the universe. But if the structure formation happened this fast, perhaps inflation wasn't as influential as thought, or it operated under principles that are still unknown. This finding could even offer indirect clues about the pre-Big Bang state of the universe, an area of cosmology still wrapped in uncertainty and speculation. The scientific community is at a crossroads. Webb's discovery has opened a door that cannot be closed. The questions it raises are not easily answered, and the solutions may require the most fundamental rethinking of physics since Newton's laws were upended by Einstein's. It is both a terrifying and exhilarating time for science. Terrifying because so much of what was assumed to be certain is now in question. Exhilarating because such moments of disruption are often precursors to great leaps in understanding. For now, the James Webb Space Telescope continues its vigil in the cold vacuum of space, gathering data that may rewrite textbooks and redefine what it means to know the universe. It has shown us that the cosmos is even stranger, more dynamic, and more mysterious than we dared to believe. In doing so, it has reminded us of the vast unknowns that still await us, and of our persistent drive to reach deeper, look farther, and question everything we thought we knew. The implications stretch beyond the realm of academic science. They touch on humanity's place in the universe. If the story of the cosmos is more complex and rapid than expected, it forces us to reconsider the timeline of cosmic habitability. Did planets form earlier too? Could life have arisen sooner somewhere else in galaxies far older than we ever expected? If mature galaxies existed when the universe was still a toddler, perhaps the conditions for life followed suit. Perhaps the universe has always been more fertile for complexity than our slow-evolving models dared to believe. What the James Webb Space Telescope has found is not merely an anomaly, it is a cosmic scream echoing across billions of years, telling us that our story of the universe is incomplete. It is a call to action for the next generation of physicists, astronomers, and thinkers. The cosmos has once again humbled us with its vastness and surprise. And just like those early galaxies, we must now evolve faster than we thought possible to meet the challenge of understanding the true nature of reality. The significance of this revelation stretches far beyond the surface observation of early massive galaxies. With every layer peeled back, new complexities emerge, each challenging foundational assumptions about time, matter, and the very nature of cosmic order. What the James Webb Space Telescope JWST has done is not only unveil a collection of ancient galactic entities, but also initiated a cascade of unanswered questions that dive deep into the core mechanics of universal evolution. A particularly disturbing aspect of these early galaxies is their apparent isolation from the expected chaotic, turbulent environment of the early universe. Theoretical predictions had long suggested that the first few 100 million years post-Big Bang would be dominated by high-energy radiation, frequent collisions, and matter still struggling to clump together under the newly forming scaffolding of cosmic filaments. And yet, the galaxies discovered appear in settled formations, displaying order, coherence, and balance in a universe that should still have been wildly unstable. This quiet maturity, this cosmic composure, hints at mechanisms of organization that may not align with anything we've calculated so far. The very distribution of these galaxies presents another enigma. Their spacing suggests that matter may have clumped together more efficiently than current gravitational models account for. Standard simulations of cosmic evolution predict the gradual emergence of large-scale structures like galaxy clusters and superclusters from initial quantum fluctuations. However, if galaxies of significant mass already populated the universe within its first few 100 million years, the pace of structure development must have been far more rapid. Either the initial conditions of the Big Bang were drastically different than assumed, or an unknown accelerant beyond dark matter or energy must have played a role in cosmic assembly. Moreover, the consistency in morphology among these ancient galaxies adds another twist. Instead of chaotic, amorphous blobs of stars and gas expected in such an early stage, several galaxies show definitive shapes: disks, bulges, and even rudimentary spiral arms. This implies that not only did they form fast, but they also had internal processes capable of organizing stars into stable orbits, processes that we thought would require billions of years of gravitational relaxation and evolution. In some galaxies, there's evidence of dust lanes, thick bands of interstellar material that typically result from multiple generations of stars living and dying. This is more than just unexpected. It suggests a level of chemical and structural evolution that should have taken far longer to manifest. This chemical maturity raises another specter. Where did the time come from for such enrichment? The presence of heavy elements, what astronomers refer to as metals, implies that multiple stellar generations had already occurred by the time these galaxies were observed. But stellar evolution, especially for lower mass stars that produce a rich variety of elements, is not a swift process. It unfolds over hundreds of millions or even billions of years. If all this happened within just a few 100 million years of the Big Bang, the implication is that either star formation began significantly earlier than we think, or stars were forming, living, and dying at rates previously deemed impossible. Another extraordinary possibility, lurking at the edge of current debate, is the idea that time itself may not behave in a uniform linear manner on cosmic scales. What if, in the young universe, time flowed differently due to density gradients, relativistic distortions, or quantum gravitational effects? While speculative, such ideas are beginning to gain traction in light of evidence that clearly doesn't fit within the boundaries of existing theory. If time was dilated or warped in the primordial cosmos in a way we haven't yet fully understood, then the notion of 300 million years post-Big Bang could carry different physical meanings than we currently assign to it. Complementing this is the re-examination of the cosmological constant, the factor that accounts for the universe's rate of expansion. Since the late 1990s, dark energy has been the reigning explanation for why the universe's expansion is accelerating. But these new galactic observations might suggest that dark energy behaved differently in the early universe. Perhaps its influence was weaker or stronger than predicted, altering the rate at which matter came together and galaxies formed. This variability, if confirmed, would fundamentally challenge the idea of the cosmological constant being, well, constant. Also deeply affected by this discovery is the long-standing theory of hierarchical galaxy formation. That theory holds that small objects formed first and then gradually merged to form larger galaxies. But what Webb is observing doesn't conform to this idea. Instead of witnessing a sea of small merging clumps, it's revealing massive galaxies already intact. This raises the possibility that large structures could form in parallel with small ones, or that under certain conditions, galaxy formation can skip intermediate phases entirely. That would require an overhaul of not just one model, but a chain of interlinked theoretical frameworks involving star formation, gas dynamics, dark matter distribution, and feedback processes from early stellar populations. One hypothesis that is starting to gain attention is the notion of primordial black hole seeding. If black holes could form directly from high-density fluctuations in the early universe, bypassing stellar evolution, they could have served as anchors for early galaxies, drawing gas and dust together rapidly through their immense gravitational pull. These black holes would effectively act as cosmic accelerators of galactic formation. While theoretical for now, the presence of supermassive black holes so early on gives this idea a new sense of urgency. If primordial black holes are real and common, then the entire cosmic timeline could be much more compressed and dynamic than we've believed. Webb's findings also put pressure on our understanding of dark matter, that elusive and invisible substance believed to constitute about 85% of the universe's total matter. Dark matter is essential in simulations to explain how galaxies stick together and how they form in the first place. If galaxies are forming earlier and faster than simulations predict, this could point to properties of dark matter that we haven't yet incorporated into models, such as a higher rate of interaction or even the ability to clump more aggressively in the early universe. This in turn might point toward a non-cold dark matter paradigm, such as warm or self-interacting dark matter, radically reshaping the cosmological landscape. Another tantalizing prospect is that we may be seeing the effects of unknown physics operating in the early universe. Theories involving exotic particles, extra dimensions, or modifications to gravity itself may finally find traction in this new empirical data. Models that have languished on the theoretical fringe, such as those involving variable speed of light, scalar field-driven cosmologies, or even entirely cyclic universes, may now deserve a second look. These were once considered fringe hypotheses, lacking observational support, but the boldness of Webb's discoveries may elevate them from speculative to necessary. What's more, these findings create tension with the observed cosmic microwave background CMB, the faint afterglow of the Big Bang, captured in exquisite detail by missions like COBE, WMAP, and Planck. The CMB provides a snapshot of the universe at just 380,000 years old, long before the galaxy's Webb is observing. The properties of the CMB tightly constrain the density, temperature, and uniformity of the early universe. Yet the presence of such massive and structured galaxies shortly thereafter seems incompatible with those constraints. Reconciling these two sets of data, both extremely precise but seemingly at odds, may be one of the most complex challenges modern astrophysics has ever faced. The technological implications of these discoveries cannot be overstated. The James Webb Space Telescope, after years of delays, budget overruns, and logistical challenges, has proven itself to be not just an astronomical instrument, but a paradigm-shifting device for humanity. Its capacity to look deeper into time and space than any instrument before it has inaugurated a new era of observational cosmology, and yet it has only begun its mission. These initial findings may represent just the tip of the iceberg. The deeper Webb looks, the more galaxies it uncovers, the more it may unravel our current narrative of cosmic history. Beyond the scientific and theoretical implications, there's a deeply human element to all of this. For centuries, humanity has been guided by a progressive understanding of the cosmos. From the geocentric model to heliocentrism, from Newtonian mechanics to relativity, from a static universe to the Big Bang. Each step brought us closer to comprehending our place in the vast expanse, and yet, each major leap was precipitated by a moment of uncertainty, a moment when new observations broke the back of old ideas. We may be living in such a moment now, witnessing a turning point where the fabric of reality as we understand it is about to be rewritten. These early galaxies are more than ancient light. They are messages from the deepest time, carried across billions of years to land in our detectors and shatter our confidence in what we thought was certain. In doing so, they reignite the spirit of discovery, the relentless pursuit of knowledge that defines science at its best. The questions now cascading from these discoveries will require a concerted, multidisciplinary effort. Particle physicists, cosmologists, theoretical physicists, computer modelers, and observational astronomers must collaborate in ways that transcend traditional academic silos. New models must be tested, new simulations run, new instruments planned. Even within this process of scientific recalibration, there's something oddly poetic. That the universe in its earliest stage, when stars were first igniting and structure was just beginning, already bore the seeds of complexity, beauty, and order. It challenges the assumption that simplicity precedes structure, that the cosmos unfolds like a slow crescendo. Perhaps instead it bursts into motion like a symphony already in progress, with rules and rhythms we have yet to fully grasp. As the James Webb Space Telescope continues its mission, more light from these ancient epochs will flood in. Each pixel of data may carry within it a story that redefines the boundaries of science. The galaxies that shattered physics may only be the first wave. Behind them could lie entire populations of yet stranger systems, hyper-dense star clusters, massive voids, or anomalies that bend space and time in ways that currently reside only in the domain of science fiction. One cannot help but marvel at the sheer audacity of the universe. Just when it seemed we were on the verge of understanding its origins, it delivers a mystery so profound it makes our greatest theories feel like half-finished sketches. In doing so, it reminds us that the pursuit of knowledge is never complete, that even the most carefully drawn models are only stepping stones to greater truths. Webb's discoveries have injected a new vitality into the scientific community, a collective sense that we are standing at the threshold of a deeper cosmic revelation. The telescopic eye that now gazes across 13 billion years of space is not just capturing images, it's collecting secrets. And as each secret is revealed, we find ourselves both humbled and uplifted. We are witnessing the dawn of a new age of cosmology. And as daunting as it may be, there is perhaps no greater privilege than to be alive at the very moment when the universe is rewriting its own story. If the James Webb Space Telescope has proven anything beyond its sheer technical prowess, it's that the universe is not merely more complex than we imagined, it is fundamentally stranger. As the data continues to stream in, it's becoming increasingly evident that the early cosmos defies not just timelines, but also the nature of causality, structure, and the principles that underlie physical law. These revelations do more than challenge cosmological models. They provoke a deeper inquiry into whether the framework of observable physics is even complete. The mathematical scaffolding supporting modern cosmology is built upon assumptions about symmetry, entropy, conservation, and temporal progression. But when a system like the early universe exhibits high levels of organization before sufficient time has elapsed for known physical laws to produce that organization, it calls into question whether our interpretations of these laws are universally applicable. For instance, if galaxies appear mature at epochs when star formation should just be emerging, Perhaps star formation itself operates under different rules in extreme conditions. It's possible that the energetic environment of the early universe acted as a catalyst, enabling processes at a quantum or subquantum scale to accelerate far beyond standard expectations. One area now receiving renewed attention is the role of quantum fluctuations and the inflationary field that presumably dominated the universe shortly after the Big Bang. Inflation is theorized to have smoothed and expanded the universe in a fraction of a second, but its precise behavior remains speculative. Webb's observations may suggest that inflation left behind regions of density contrast far more significant than anticipated, leading to localized bursts of rapid matter organization. If true, this would mean that while the universe as a whole obeyed the expected inflationary trend, pockets of accelerated evolution may have seeded galaxies almost instantaneously after inflation ended. These could be the early beacons Webb is now detecting, products not of a uniform early universe, but of a lumpy, uneven one punctuated by zones of anomalous energy density. This opens the door to the idea that the universe's early development was not governed solely by broad, overarching laws, but also by localized quantum conditions. This quantum localization could mean that different regions of space, now separated by billions of light years, evolved under slightly different rules in those crucial early moments. If so, what we call laws of physics might be more like statistical averages, rather than hard and fast rules that apply universally. In other words, physics as we know it could be a general case, but not the definitive account of what happens under the extreme initial conditions of the universe. This also places new importance on the concept of cosmic variance, the idea that what we observe is just one realization of many possible cosmic configurations. If the universe contains areas that develop differently, then our observable universe might be an outlier. The galaxies that formed rapidly could represent areas where initial conditions were atypically conducive to early complexity. These wouldn't invalidate our existing physics entirely, but would limit their predictive power to a statistical subset of cosmic history. This would be a profound shift, suggesting that the cosmos isn't uniform in its compliance with physical laws, a notion that would require the reformation of fundamental cosmological theory. Further unsettling is what this might suggest about the possibility of multiverses. If different regions of the cosmos, especially in the inflationary aftermath, manifest distinct physical behaviors, then the argument for a multiverse or a cosmic landscape of variable laws and constants gains unprecedented weight. The presence of fully formed galaxies so early might not just reflect anomalous evolution, but the actual fingerprint of a neighboring set of physical parameters, a different corner of the inflationary field's potential landscape that briefly intersected our own observable space. If this is true, Webb's discoveries are not merely rewriting the history of this universe, they're offering the first tangible data points from a broader cosmological tapestry of parallel or adjacent realities. Another line of inquiry gaining traction is whether the early universe was influenced by particles or fields that have since decayed or disappeared. Known as early dark energy models, these propose that additional forces or particles existed for a brief window of cosmic history and contributed to rapid structure formation before vanishing. These particles would not be present today and would therefore leave little evidence other than their effects on early galaxy formation. If Webb's galaxies are the results of such fleeting influences, then we're being offered a rare glimpse into a lost chapter of cosmic evolution, one that might be irrecoverable except through these ancient signals of light. The concept of time itself is now being examined from new perspectives. In standard relativity, time and space are interwoven and elastic, shaped by the mass and energy within the universe. But what if time, as experienced by matter in the early universe, unfolded differently? Not just faster, but along nonlinear trajectories. Some speculative models in quantum gravity suggest that at high energy densities, time may have exhibited fractal or layered characteristics. If the flow of time was non-uniform or multidimensional in the universe's first few million years, then the development of galaxies could have taken paths through time that bypass the straightforward chronological sequence assumed by current physics. Such models are still in their infancy, but they may hold the key to explaining how systems we see as premature could have evolved along alternative temporal contours. Compounding these mysteries is the realization that the Webb telescope is revealing large-scale coherence in galactic distribution far earlier than expected. The structure of the cosmos today, the cosmic web of galaxies and voids, is believed to have developed through gravitational attraction and dark matter scaffolding over billions of years. But if coherence already existed within a few hundred million years, then the origin of this order must stem from processes that predate conventional structure formation. This pushes theoretical physicists to consider the role of pre-Big Bang conditions or boundary states. Speculative frameworks like conformal cyclic cosmology or quantum loop cosmology, where the universe is not born from nothing, but emerges from a transformation of a previous state of reality. This further fuels the idea that the Big Bang itself may not have been the singular origin point we have long imagined. Instead of an abrupt explosion from a singularity, the cosmos could have emerged from a transition phase in a cyclical or rebounding cosmological model. These early, mature galaxies might then be the inheritors of patterns or structures seated in a prior cosmic epoch, meaning that what we are seeing is not the beginning of everything, but the continuation of a deeper, perhaps eternal process of cosmic evolution. This would demand a philosophical as well as scientific revolution as our narrative of origin shifts from one-time birth to eternal recurrence or quantum emergence. What's increasingly clear is that our current instrumentation, as powerful as it is, may still be only scraping the surface. Webb's revelations have demonstrated the transformative potential of infrared astronomy, particularly in the realm of early universe exploration. Future missions may need to focus not only on even longer wavelengths to push further back in time, but also on broader spectrum instruments capable of detecting signals from hypothetical particles, primordial gravitational waves, or other exotic byproducts of early universe processes. Missions like the planned Nancy Grace Roman Space Telescope, the extremely large telescope ELT, and proposed successors to Webb may now need to reorient their designs to accommodate questions that have only emerged in the wake of these findings. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on this discovery? What do you expect Webb found? We want to hear from you. Thank you for watching and see you next time.